Look around you right now. The building you're in, the car you drove here, the phone in your pocket, the bridge you crossed this morning without thinking about it. All of it. Every beam, every frame, every hull, every bolt started as this. Iron ore, a crumbling red rock, the same rust you'd scrape off an old nail. The iron is in there, locked in chemical bonds with oxygen, useless in that form. Before it can hold up a skyscraper or carry a container ship across an ocean, something has to break those bonds. Something violent, something precise, something that hasn't fundamentally changed in over 800 years. This is a blast furnace. And by the end of this episode, you'll understand exactly how it turns that crumbling red rock into the backbone of modern civilization. Steel is the most widely used construction material on Earth. Close to 2 billion tons produced every single year. In the United States, that works out to roughly 575 pounds for every person alive. In China, that's over 1,500 pounds per person, just to give you some perspective. There are two ways to make steel. The electric arc furnace melts recycled scrap, using massive electrical current, efficient, clean, and growing fast. But scrap steel is a finite resource. You can only recycle what already exists. And the world needs more new steel every year than scrap alone can supply. When you need to make steel from scratch, from raw iron ore pulled out of the ground, there is still only one process capable of doing it at the scale the world demands: the blast furnace. More than 70% of all steel produced today still comes from this route. Not because we haven't thought of alternatives, but because nothing else can even come close to competing with this process. The first blast furnaces in Europe appeared in Sweden in the late 1100s. Stone towers built against hillsides so workers could haul raw materials to the top on foot and drop them in. Crude, slow, and completely dependent on one fuel: wood charcoal. It took 5 tons of charcoal to produce a single ton of iron. Making iron meant consuming forests, and as demand grew, the forest shrank. By the early 1700s, Britain faced a crisis. Not a shortage of iron ore, a shortage of trees. In 1709, an ironmaster in Shropshire named Abraham Darby solved it. He discovered that coal, baked in a sealed oven for 18 to 24 hours, produced a fuel called coke. Coke burned hotter than charcoal, was strong enough to support heavier furnace loads, and required no force at all. There was one catch. Early coke contained enough sulfur that the iron came out too brittle for most uses, initially only good for casting pots and pans. It took decades to refine, but once they did, the Industrial Revolution had its engine. Then in 1828, a Scottish engineer named James Neilson added the next leap. He preheated the air before blasting it into the furnace. Obvious in hindsight, but revolutionary at the time. Hot blast cut fuel consumption by up to 2/3. In 1859, Alfred Cowper developed regenerative stoves that captured the furnace's own waste heat and used it to preheat the incoming air. The furnace was now recycling its own exhaust to feed itself. Those 3 inventions, coke, hot blast, regenerative stoves, are still the foundation of every blast furnace operating on Earth today. Before we go inside, let's understand the scale of what we're looking at. A modern blast furnace stands 30 meters or more tall, about the height of a 10-story building. Its inner volume can reach 6,000 cubic meters. The base can be up to 16 meters across. The shape is 2 cones joined at their widest point, intentionally designed, so materials can expand as they heat and descend, then concentrate as they melt toward the base. Every dimension is engineered for a reason. Inside, the walls are lined with heat-resistant refractory brick and carbon blocks capable of lasting 15 to 20 years before replacement. At the base, a ring of copper nozzles called tuyeres injects preheated air directly into the coke bed. They are made of copper and they survive internal temperatures exceeding 2,000 degrees only because they are continuously flooded with cooling water. Stop the water for even a short time, the tuyere melts. Those massive cylindrical structures standing beside the furnace, called Cowper stoves, burn the furnace's own exhaust gas and use that heat to preheat the incoming air blast to up to 1,300 degrees Celsius. 3 or 4 stoves cycle continuously, so the blast is always hot. Here is the one concept that makes everything else make sense. A blast furnace is a countercurrent reactor. Solid materials, iron ore, coke, and limestone, are loaded into the top and descend slowly toward the bottom. At the same time, hot gases generated at the base rise rapidly toward the top. They meet in the middle. Heat transfers. Chemistry happens. By the time the solids reach the bottom, the iron is molten. By the time the gases reach the top, they have stripped away the oxygen and carry the waste products out. Now here is the detail that stops most people cold. The solid materials take 5 to 8 hours to travel from top to bottom. The gases traveling in the opposite direction make that same journey in 6 to 10 seconds. And those gases are not drifting upward. They move at 30 to 60 meters per second, nearly 130 miles per hour, a hurricane-force wind driving upward through a column of solid rock that is simultaneously sinking under its own weight. At the base, the hot blast ignites the coke in a violent zone called the raceway. Temperatures here reach between 1,900 and 2,300 degrees Celsius, hot enough to vaporize most metals on Earth. On some furnaces, there is a small window on the tuyere called a peep sight. Engineers can physically look through it and see the raceway, with white-hot coke swirling in the air and blasts like a luminous storm. That combustion produces carbon dioxide, which immediately reacts with surrounding hot coke to become carbon monoxide. Carbon monoxide is the real chemical agent of this entire process. As it rises through the descending ore, it strips oxygen in stages. Hematite becomes magnetite. Magnetite becomes wustite. Wustite loses its final oxygen atom and becomes metallic iron. Freed from the ore, it has been locked inside for millions of years. As the iron sinks deeper and temperatures climb past 1,200 degrees, it absorbs carbon from the coke, which lowers its melting point. It liquefies. Droplets trickle down through the coke bed and pool at the very base, an area called the hearth. The liquid slag, all the impurities drawn out by the limestone, floats on top of the denser iron. They separate naturally, like oil and water. Every 2 to 5 hours, a drill punches open a tap hole in the furnace wall. Molten iron at over 1,425 degrees Celsius pours out in a river of orange light into torpedo-shaped railway cars, each holding hundreds of tons, bound for the steelmaking plant. What you have just seen is the process working perfectly. The reality is more precarious than it looks. Inside the hearth, at the very center, sits a stationary cone-shaped pile of coke that never moves and never feeds the fire. Engineers call it the deadman. It simply sits there, surrounded by flowing liquid iron, supporting the weight of the entire material column above it. Here is the counterintuitive part. That pool of liquid iron pushes upward, buoyancy forces acting on thousands of tons of solid material above. If the liquid level gets too high, that upward force can stall the descent of the entire 30-meter column of solids. The furnace freezes from the bottom up. And there is a risk even more costly than that. A single undetected water leak in the cooling system can chill the entire hearth, solidifying thousands of tons of molten iron into one solid block. Getting a chilled furnace back online can take weeks of dangerous oxygen lancing. It is one of the most expensive accidents in heavy industry. This is why modern furnaces run continuous monitoring, driven by artificial intelligence, gas temperature, pressure, exhaust composition, liquid levels, dozens of variables, every minute, around the clock. A process born in the 1100s, now kept alive by machine learning. What pours out of the tap hole is called pig iron, and the name has a story. Historically, molten iron flowed down a central channel into rows of smaller side molds. Workers thought it looked like piglets nursing from a sow. The name stuck for 3 centuries. Pig iron is 4.1 to 4.4% carbon, and that is the problem. It makes it brittle. Drop a piece and it shatters. That is not something you build a bridge with. So the pig iron travels while still molten to a basic oxygen furnace, where a supersonic lance blasts pure oxygen into the liquid metal. The oxygen burns off the excess carbon. For structural steel, it drops below 0.3%. For different grades, carbon is precisely controlled between 0.008 and 2.1%. That number, the carbon percentage, is what determines whether you are making a bridge beam, a surgical instrument, or a coiled spring. Let me put the scale of this in perspective. A blast furnace in the 14th century produced 1 ton of iron per day. A modern giant furnace produces over 16,000 tons in that same time. One modern blast furnace consumes the same net energy as a 1.75 gigawatt nuclear power plant every single day. And yet the process extracts iron with extraordinary efficiency. The slag that pours out alongside the iron contains almost zero iron oxide, proof that the furnace has captured essentially every useful atom from the ore. And that slag is not waste. Depending on how it is cooled, it becomes road aggregate, a key ingredient in cement, mineral wool insulation, or glass-making raw material. The byproduct of iron production is quietly inside the walls of your house. Here is the uncomfortable truth. A blast furnace is fundamentally a machine that converts iron oxide and carbon into iron and carbon dioxide. That chemistry cannot be avoided. Carbon is not just the fuel here, it is the chemical agent. You cannot swap in renewable electricity the way you might with other industries. Producing 1 ton of steel this way generates approximately 2.33 tons of CO2. Across 2 billion tons of annual production, that is why iron and steel account for 7 to 9% of global greenhouse gas emissions. 3 approaches are being tested at scale right now. Top gas recycling captures furnace exhaust, strips out the CO2, and re-injects the remaining gases back in as fuel, reducing coke consumption. Carbon capture and storage attached to existing furnaces could deliver major reductions in emissions without replacing the furnace itself. And direct reduced iron, or DRI, replaces coke with hydrogen entirely. No carbon monoxide, no CO2. Sweden's Hybrit project produced the world's first hydrogen-reduced steel in 2021. If powered by renewable energy, the only byproduct is water vapor. But here is the scale reality. Global investment in coal-based blast furnace capacity increased by 5% in 2026. The blast furnace is not going away. It is being reinvented, slowly at enormous cost, under enormous pressure. A stone tower in a Swedish hillside, the 1100s. Abraham Darby burning coal in 1709. James Nielsen heating the air in 1828. Alfred Cowper recycling the exhaust in 1859. And today, a 30-meter tower managed by artificial intelligence, consuming the energy of a nuclear power plant, producing 16,000 tons of iron every single day from a pile of rust and 3 ingredients. That is the blast furnace, one of the half-dozen fundamental machines of industrial civilization, and the reason the modern world looks the way it does. If this is the kind of infrastructure that fascinates you, subscribe, and we'll see you in the next episode.